What could be the next option for this detection medium? And these are solid state detectors. And solid state detectors could be a scintillator or silicon. As I have said already, there are many type of detection medium, but we will consider only those detection medium which might be needed to understand Alice detectors only. So keeping that thing in mind, let us have a look little bit about on these scintillators. So what is scintillators? Scintillators, I mean, are some detecting medium which based on some material which exhibits scintillation, usually in the form of ultraviolet or visible light, when excited by an ionizing particle. Just look at the schematic shown in this page. So when a charged particle or ionizing particle enters this media, it is exciting within this medium and producing a photon. And this photon, the next job is to, collect this photon and produce a measurable signal. What is the measurable signal? What could be the measurable signal here? After this, photon production, you need to take this photon, put it into the photocathode, and it will produce some electrons. It will be multiplied by diodes if you have, and then this electrical charge will be appeared in your readout electronics in the form of a pulse, and that is what you will measure. So by scintillation, what we do when a charged particle or ionizing particle enters, a light will be produced, and this light will be converted into a number of electrons, and those electrons will produce a pulse. So once pulse means some incidence, and there is a relation between this pulse and the incidence. By incidence, I mean the energy deposition. So there is some sort of linearity, and from this linearity, one can measure the characteristics of the incident particle. Okay, and usually these scintillators are very fast, and that's why when in kind of complex experiment, the scintillators are of first kind of choice for trigger detectors. And there are many type of scintillators. For example, this plastic, sodium iodide, and so on. And among these, the most common scintillators in our field is a plastic scintillator. Of course, this lead tungsten are also there. And if you are now, if you understand this scintillator, let us go over to the next one, which is a silicon. What is silicon? This is a special type of solid state detector, which is called a semiconductor. What will happen inside this semiconductor detector? And inside semiconductor, these molecules or atoms, they are bound by covalence bond. Usually, they have 4 hands. They join together to form a bigger lattice. And if you, if you calculate, then the energy levels, they will form energy band. They will form energy band. One is conduction band, another is this valence band. Okay, and they if it is a semiconductor, there will be a certain gap between these two. So when a ionizing particle enters, it will knock out one of the electrons from the valence band and create a vacant site, which is called as the hole. And this knocked out electron will go to the conduction band and will be free to move. Now, if you apply some voltage across this semiconductor, then depending on the charge and the type of the electrode, electron will move in one direction and the holes in the other direction. Actually, holes don't move, rather electron will move, but it seems that hole is moving. But if you calculate when you apply the voltage, and if you calculate the total current, probably you will find nothing, because total number of these electrons and holes are same. If it is a pure semiconductor, then what you need to do? You need to dope some other material. For example, it could be a p-type or n-type. What are the p-type? These are boron, aluminum, gallium, indium, etc. And for n-type, these are phosphorus, arsenic, and so on. What will happen if you add some n-type impurities to this semiconductor? They will add more electrons to the system, and effectively you will get a resultant current when you apply the voltage, and as a result, we will get a output, current or pulse. So summarizing what we will find, I mean, the most important part for the silicon, there could be other semiconductor detector, for example, germanium and so on. But the most interesting part for silicon is it can be used at room temperature. And usually the energy deposition is large. Why large? Because usually these solid state detectors are much more dense compared to gas detectors. So you expect more energy depositions when these ionizing particle enters and interact. And they can be very thin. Thin means less energy depositions for longer period, so it will last long. So in that sense, it will be I mean, long lived. This kind of detectors you don't have to worry once installed for quite some period. So in that sense, they are radiation hard. And diffusion effect smaller than in gas detector. You know that once charge created in gas detector, they will travel along. But in case of semiconductor, they don't. They will travel very little, and so they have a very good position resolution. So don't expect the other, nearby things to be to get disturbed, and that's why one can achieve this very small position resolution, such as 10 micron. As I was saying, that large energy depositions will occur, and also one important thing for this semiconductor detector is the ionization energy is very less compared to gas. In case of gas, if you remember, it is about 30 keV to produce electron ion pair, but in case of semiconductor, it is very less, 3.6 only. Now if you divide this divide this total energy deposition by this 3.6, you can calculate the total number of electrons or electron holes pair produced, and accordingly you can calculate the signal strength. But one disadvantage one can say is, compared to gas, is there is no as such amplification as is there in case of gas detector. There is avalanche and so on, so the signal strength is very high. But in case of semiconductor, there is no as such intrinsic gain. That's why you need to have a very good P amplifier attached or next to the detector, or you need to suppress the noise substantially so that your signal don't get lost. Okay. And in silicon, you can have very tiny detectors, segmentation to a very small one. So basically you can have very large number of detectors within very small area. So you can have many pixels, which you cannot achieve in case of gas detector. Moreover, this higher carrier probability. And these semiconductor detectors are pretty fast, and their response time is of the order of 30 nanoseconds or even less. And large power consumption required. Here in case of gas detector, this don't happen. In case of solid state detector, it do. So you need to cool these detectors from the outside to make it reasonably working well. And one disadvantage for the silicon detector compared to gas detector is its cost is a little bit high compared to gas detector. I would like you to calculate one very important thing, and please take it as your homework. An intrinsic silicon will not work to serve the purpose of a detector. You need to add some impurity. Why? Just your homework is you have to calculate the MIP signal. A minimum ionizing particle is entering. It is depositing some energy. You can take the thickness of the silicon as 300 micron and calculate what should be the MIP signal to the thermal contribution. This is your homework. And this picture I have shown, this has been produced indigenously at Bale, and we have several test beam. We have tested these detectors at lab and beam lines, etc., and have beautiful results. But this is not the right place to discuss those things. Now let us go over to to the next slides, where little more advanced in terms of for the silicon detectors, in terms of segmentation. Technology had advanced. This technology had really advanced in terms of the silicon detectors, where one can go segmentations in the level of micron. Usually when we started back in 2010 or so, there we used to really struggle to get 1 centimeter square, segmentation for silicon detector, really hard. It was really hard. But later on, the technology came up very fast. And now in our field, we can easily achieve silicon detector with segmentation up to few micron. And this was possible because of this CMOS-based MAPS technology. And what is this MAPS? MAPS is CMOS-based and is, the most beautiful part of this MAP technology is it is CMOS-based and is in synergy with the industry. That's why cost has reduced to order of magnitude. And moreover, because this MAPS technology, they are doing this detector part in a very thin layer. And also, not only the detector part, the associated front-end electronics are also implemented within the same volume. Because with this technology, they can shrink the dimension of the transistor. So as a matter of fact, what will you achieve? You have sensors plus immediate front-end electronics within the same extent of the silicon, tiny silicon chunk, and get a very small amount of material budget as well. So very radiation hard, cost is low, very high granularity. So you are in very good shape as far as your detection medium for very highly dense environment is concerned. Okay. So at least if somebody tells you that MAPS is there, instead of usual silicon technology, where somebody is telling you that we are using MAPS, it means they need very high granularity because they might need to measure a lot of particle within a very small area. Okay. Okay. If now you are a little bit aware about this CMOS, then let us go over to the next one. With this CMOS, the most simplest part is in terms of measurement. You don't need to worry about the energy deposition. Just let a particle enter the CMOS, it will heat, and this heat information will be stored. And this number of hits N is directly proportional to the signal you are getting out of the detector. So now, unlike earlier case where your signal is proportional to the energy deposition, here your signal is proportional to the number of hits. Okay, and there is a linearity relationship hold between this N and signal. So you can find a relationship N as a function of E, and this can be used for tracking or even for energy measurement as well. And that's why this MAPS technology has been adopted very severely, not only in tracker these days, but also in calorimeters. Okay. From these, gas detectors and solid state detectors, there are other methodologies as well. Think of a situation, a particle enters a volume, and in this volume, there is a plane where it gives some hits. And let the particle go, traverse through, traverse some path length, and then, keep another layer of medium, which will record another hit. So you can calculate two events, and you know the distance between these two planes, and you know how much time the particle took. And from this, using this formula for this delta t traveled by the particle between these two events, one can calculate this delta t as a function of the momentum of the particle and also mass. If you have two particles passing through these two layers, say M1 and M2, the time difference will be can be expressed with this formula for delta t. If it is a single particle, then one can calculate the mass. One can calculate the mass. It means this type of methodology can be applied for particle identification, and there could be error in this mass measurement from different sources. It could be the momentum of the particle itself, the length between these two events, and also the time. Here, the length I am saying this length could be two events placed. I mean, because of the two layer of the detector, it not necessarily like that. It could be the vertex from where the particle is coming and only one plane. Okay, and then let go back to the another mechanism. This is called transition radiations. What is transition radiation? When a charged particle passes through an inhomogeneous media at the boundary, depending on the moment of the particle, they will radiate some electromagnetic radiation. And what is the energy that it will radiate? This can be expressed as W equal to 1/3 alpha H cross omega P gamma. Gamma is this relativistic factor, and omega P is the plasma frequency, which can be represented as in the right hand side, H cross omega P. And once you know this amount of energy emitted, then you can calculate what is the how many photons it will be radiated when a high energy charged particle passing through a boundary between two media. This is this total energy radiated divided by the energy of a photon. Okay, and this is directly proportional to the alpha. Usually, for this boundary, people used to use different kind of transparent media, which should be transparent to the emitted photon. Otherwise, what will happen? At the boundary, when the radiation is coming out, if the medium itself will absorb this radiation, things will be lost. So we have to choose such material which will, at the boundary of which radiation will come out, but this medium will not going to absorb this radiation. So this choice of radiator is very much important. And I have given two pictures. These are the material which have been used in case of transition radiation detector in ALICE. I will come to it later on. Well, the left side is a kind of foam, and right side is kind of a fiber, polyethylene fiber. Now, if you look at the radiated energy spectra in terms of omega and the cone, then this is the expressions one can achieve. So if you want to have some kind of say radiator, or if you want to design this transition radiation detector, what kind of photon detector you need to consider, you have to look at this d2w by d omega, d capital omega. This will directly give the amount of energy radiated as a function of frequency for a particular solid cone. Okay. So it's a lot to know about detection medium and how they will be detected, different methodology. Now let's go over to the ALICE once again. Already we know the ALICE. We know what it stands for. We know what it meant for, and so on. But to start with ALICE, the best starting point would have been this beam pipe in ALICE. You know that at LHC there are two beam pipe in which directed beam go round and round. They will collide at certain points. ALICE is one such point where these two beam crosses each other. This point is called interaction point, and that they collide. So before designing of your ALICE detector or understanding this ALICE detector, it is better if you have little information about this, how this beam pipe look like. So I have zoomed the crossing point in the right side, this schematic, where see two beam pipe are crossing at a very, very fine point, which is called the interaction point. Now, when you are looking at the beam pipe, there are two requirements. One requirement is from the machine which is delivering beam. Another requirement is from the experiment you are designing. So ALICE demand maximum transparency to particle. So beam pipe should not be of very, high dense material. So least dense material could be beryllium. That's why at experimental sites, these beam pipe are made with beryllium. In other points, I mean, in rest of the places, they are not made with beryllium. They could be copper or stainless steel. And then limited beam gas backgrounds conformity with the environmental and installation constants. This is the requirement from your experiments. And what is the constant from the LHC point of view? The machine which is delivering beam, they need safe operation. So, I mean, even if you want to know your beam pipe could not be of very hard material, they will say no. You have to keep the vacuum. You have to make sure that radiation should not come out and harm other things. That's why, I mean, the safety is very much important. And at the same time, the beam aperture need to be continued. So, keeping these two in mind, at Alice experimental site, this is the parameters for the beam pipe: diameter, wall thickness, and length. Earlier, before this present lockdown, I mean shutdown, long shutdown, LS3, before this long shutdown, the diameter was about 60 mm, wall thickness was about 800 micron, and length was about 5 meter. But because of high luminosity beam, I mean, the LS will going to deliver in this run 3, the beam pipe need to be modified at experimental sites. Keeping that in mind, so during this LS2, this beam pipe has also changed. See, its diameter is now very less. Instead of 60, it is about 38. Wall thickness, I mean, remains same, and length is little bit increased. This length, the length I'm talking about, the length of the beam pipe at the experimental site. So if you look at the Alice beam pipe, it has three sections. One is this central section, and other is two, sections at the two sides. The central sections is made of beryllium. This is a very low dense material. It will reduce beam, and matter interaction less, and also you need, very narrower beam pipe here. Okay. So by narrowing down this beam pipe at the experimental site, what is the advantage Alice will get? Alice can put detector much more closer to the beam. Much more closer to the beam means less chance of losing particles produced at the interaction point. And that is one of the reason during this long shutdown, in our tracking systems, the closest detector system in Alice upgraded in such a way so that they can reach much more close. Okay. Once you are, once you know this construction and these different features of this beam pipe, let's go over to Alice. Alice has two, naively two type of detectors. So in the left bottom, I have shown the central barrel. This is the cylindrical part, central cylindrical part. And in this cylindrical part, there are many detectors. Starting from the beam pipe, first one is the ITS, inner tracking system. Then comes TPC, time projection chamber. Then comes TRD, transition radiation detector. Then comes time of flight detector, and then followed by calorimeters and muon detectors, right? And this is the scheme, exactly this is the scheme we have discussed at the beginning of our yesterday's lecture, how a complex detector stacking should look like. Apart from the cylindrical part, there are also forward and backward sides. In forward and backward sides, there are few more detectors. One is T0, V0. Actually, these were not now. T0, V0, PMD, FMD, ZDC, MTR, and MCH. These are the forward detectors. Some part of them may be backward detectors, as was asked yesterday by someone. Okay, now let us go through one after another. First one is the innermost detector. What was that? That is the inner tracking system. So I have put this inert tracking system ITS with a note earlier. Earlier means before this present long shutdown period. I mean, after this long shutdown period, you know that LHC had started taking data once again. I mean, it is delivering beam, so Alice started taking data. Now detectors has upgraded. So my earlier means before this upgradation, and now means what is the configuration right now. So earlier, this ITS has three type of detectors. Each type of detector has two layers. The innermost one was silicon pixel detector, then silicon deep detector, followed by silicon strip detectors. As the name suggests, these pixels has, I mean, highest granularity, they're the smallest one. Then silicon deep detectors little bit more, I mean, higher, not lower granularity, and silicon strip detector is the coarse granularity in terms of these three layers. I mean, as far as these three layers are concerned. As I was discussing at the beginning of this lecture, that we usually, when we address these detectors, we never, we never say in terms of usual length or usual velocity. Rather, we express in terms of rapidity. And that is what I have tried to show you in terms of coverage. So the innermost detector SPD has coverage 2 to 3.9. Okay. And for SDD, it has coverage 0.9 to, sorry, 0.9 to, I mean, plus minus 0.9. And SPD, I was telling wrong. So 2 to 1.4. And then SSD, this is plus minus 1. And how long they will be spaced along the radial direction. This ITS is starting from 3.9 centimeter to 43 centimeter. Just have a look. So this 3.9 centimeter is the nearmost you can go in detecting particle in the earlier configuration. What I was saying, after beam pipe modification, now the beam pipe is much more narrower, so you can go even close, much more close to the beam pipe. So instead of 3.9, in the present configuration, we will see this will probably go to half of this present value. What is the objective for this ITS? Finding the primary vertex with a resolution better than 100 micron with this earlier setup. Secondary vertex reconstruction is also necessary to, study these different kind of, say, resonance particle or others, and also need tracking and identification of low PT particles. And along with the TPC, it used to give a very good momentum and angle resolution. Now let's look how it looked like after the modification. So earlier there were three type of detector, 6 layers, each having 2 layers. Now instead of 6 layers, we have 7 layers of detectors. Okay, these and all the detectors are not usual silicon detector. Now all these silicon detector layers are made with map with CMOS technology. So detectors are very thin. They are very, highly granular. The granularity can go up to say 30 micron by 30 micron, unlike 1 centimeter square or something like this. So we can have very good position resolution. So very close by two tracks can be easily resolved with this present configuration compared to the earlier setup. And this is the most beautiful part of upgrading this. And now just see the innermost layer, layer 0. What is the what is the distance from the beam axis? This is 22 centimeter. Okay. And since we are using maps, now it can also handle lot many particles, which is one of the most important requirement as far as this ANTRI is concerned. Earlier the usually readout rate was 1 kilohertz. But now with this run 3, LHC will deliver and which will going to give a rate of 50 kilohertz for lead collection and 200 kilohertz for PP collections. And map, Alice with this upgraded inner tracking system now can easily handle this kind of rate of particle in these interactions. Okay, so this is what this ITS will work. And then just after the ITS, what is the next detector? This is the time projection chamber. Since we have already discussed that this MWPC, what is MWPC and GEM, so just to, here we will discuss about what this TPC will do and different features. So in earlier case, before this upgradation, during run 1 and run 2, TPC was equipped with multi-wire proportional counter with a gating gate. And when I am saying multi-wire proportional counter, you remember how it works. And with multi-wire proportional counter, rate capability is an issue. Maximum rate capability one can handle 3.5 kilohertz, right? Not more than that. But during run 3, LHC will deliver with a rate 50 kilohertz for lead collection. So with this MWPC, it cannot be done. Okay, we'll come back to it once again. What was the coverage for eta? This is plus minus 0.9. And what was the extent in the radial direction? 85 to 247 centimeter. What is the diameter? 5 meter. What is the stretch? It is also 5 meter. So you can imagine how much big the TPC detector was in this form. It is really big, and usually this TPC detector is the heart of any complex detector in today's high energy physics experiments. Okay, and what is the gas people used for this TPC? This is a neon carbon dioxide mixture in the ratio 90:10, and the voltage applied about 400 volt. And when I'm saying these numbers, I guess you can easily correlate from yesterday's discussion about MWPC. Not only this gas and all these things, you need to have some readout techniques. And for these readouts, it has, total 36 into 2 readout chambers. Some are called outer readout chambers, some are called inner readout chambers. And these readout chambers has pad sizes of the order of 4 by 7.5 millimeters square, and it gives, it really gives, or it really tells you, limit you the limit to which you can precisely measure in the XY plane the dimension of this pad. And how many channels are associated with this TPC? Look at this number, 557, 568, these many numbers. So when Alice is running, it means all these channels of TPC are working, they are collecting data, and these data are getting processed in a human readable form and delivered to you for later on analysis. What do this TPC do? This is the main tracking detector, as I was saying. It has very good track separation efficiency. The main thing it do is measure the DEDX, and the resolution for this energy deposition is better than 10%. Track matching efficiency 85 to 95%, along with the track matching these algorithms. And also this track finding efficiency for PT greater than 1 GeV is greater than 90%. Momentum resolution is about 2%. And rate capability I have already discussed. This is limited by this readout, and it is about 1 kilohertz. So this is the rate that is of concern to run Alice with this upgraded during run 3, where the interaction rate is expected to be 50 kilohertz. And for obvious, TPC with MWPC cannot work. So you need some upgradation. So after upgradation, how it look like? Just MWPC is replaced by GEM. So now, presently in Alice, TPC is working with this GEM-based technology. Not only the detector, also the readout electronics has also got changed. In earlier, there is some other readout methodology which were used, but now these electronics is a Sampa chip. This is very custom designed chip specifically for this purpose. As I was saying, the objective is pretty much clear. You need to improve the physics performance, need to tolerate this high rate capability in the range 50 kilohertz to 200 kilohertz for pp. And advantage is, as I have said during JM and MWPC discussion yesterday, there is no as such ion backflow. That's why the dead time for the detector is very less. So effectively, the detector will be very much capable. And I have listed the characteristics in the right hand side just below this picture for this detector. One can have a look into it, but to me this operation at 50 kilohertz is the most important, along with the IBF less than 1%. Other thing one can tune and keep in mind for future reference. Okay, so you know about this TPC now, earlier, and what is in the present scenario. Once you know this, then comes the TRD detector. By the way, just always keep in mind that when we are talking about these Alice detectors, there is a cylindrical part and then forward backward part. The cylindrical part, all the detectors are in concentric cylindrical cells. So TPC was also like that. It has a inner cylindrical cell, and say 400 centimeter away there is another bigger concentric cell. So these two cells were two plates. Think like this. And after this TPC, there is another detectors in the same form, cylindrical cell. This is called TRD, transition radiation detector. What is the main purpose? By the way, this TRD means transition radiation will come. Transition radiation detection is involved. It means there need to be a radiator. What is the radiator? For this transition radiation detector, there are two major components. One is radiator, and I was saying just at the beginning of today's talk, there is a foam, special foam, Ruachel. This is 48 mm thick and polyethylene fiber. These two are compact. These two are used to make the radiator part of this transition radiation detector, followed by MWPC detector. So never get confused. This radiator is nothing to just to extract the just to make the ionizing particle give some signal, and you need to detect the signal. And to detect the signal, people are using MWPC along with a drift region. Why drift region is required? Because you need to do three-dimensional position measurement. So MWPC will give you XY, and drift time will give you Z position. Okay. And how many deep chambers are there? There are about 540, and it has extent of 2.9 meter to 3.68 meter along the radius. So two concentric cell, one at 2.90 and other at 3.68. And what is the extent in the along the beam direction? This is about 8 meter. How many layers are there? 6 layers, and it has full phi coverage. And eta coverage is, same like TPC, plus minus 0.9. And how many electronics channels are there? About 1.16, just like TPC. So one can have, so that one can have 1-to-1 and correspondence to TPC with this TRD whenever required. And what is salient features? Salient features are good pion rejection capability, and the factor is about 100 for PT greater than 100 GeV. And then TRD has a very good momentum resolution, about 4. Optimized track efficiency, 90%. Electron identification in the central barrel for PT greater than 1 GeV. Momentum range above, I have written this region, this part 1 GB part, and then helps in studying light and heavy vector meson resonances along with ITS and TPC. As I was saying, that there need to be an synergy between this TRD and the TPC, and that is required for this. I mean, for example, heavy vector meson resonances measurement. Okay, there is no as such upgradation during this long shutdown for the TRD. So what was there now is still there. Then comes the top detector, time of flight detector. And you know, when we are saying about time of flight detector, it means there should be some detector arrangement which will sense the incident and sense the incident after some lapse of time. So it will measure the time difference. What is the coverage? The coverage is less than 0.9 for 370 centimeter to 399 centimeter, and it has full 5 coverage like TPC and TRD. And this detector is built with multi-gap resistive plate chambers. I haven't discussed this multi-gap resistive plate chambers kind of detector. I guess there will be a separate lecture on these kind of detectors. And these detectors are really very fast. They can sense things in picosecond order. That's why these top are used as trigger detector as well. And its time resolution is of the order of 50 picoseconds. At least during prototype test, they reported this. But during, this data taking, the time resolutions found was about 56 to 80 picoseconds. Okay. So it is the top. And what is next? Next part is the calorimeter. What is the calorimeter? Calorimeter is a means to measure the energy of particles, and in destructive means. So particle comes, it will absorb the particle completely and then find its energy, its direction, and so on. Usually what happens when a charged particle like electron enters the calorimeter, it will produce Wem's-Salong photon, and this Wem's-Salong photon will produce electron-positron pair, and this process go on and it will form a shower. So you can see this shower is extending in the transverse directions, and in the longitudinal directions, these secondary particles, they are produced with half of the earlier stage energy. So if you look at the longitudinal along the direction of this particle moving, the energy deposition profile, it will look like dEdt, approximately E0 T to the alpha e to the minus beta T. So one profile T to the alpha will let it increase, another profile let it decrease after some point. So it will have a Gaussian, distorted Gaussian like shape. So it will have a maximum value at some point, maximum energy deposition, and then again it will fall. And it will also have some transverse profile, and it will follow dE by dr equal to 2 exponential, combination of 2 exponential, and they have their own importance. Usually in the left hand side schematic, I have plotted few layers. Each layer consists of absorber and then detector, then electronics, and so on. So absorber is necessary to convert one electron to many electrons and photons. This is the this is the requirement for the absorber. And then you need to put a detector to sense these particles. Usually in today's calorimeter, most of the cases, the silicons are used. And during choice of absorber, one need to keep in mind they need to be very dense, very thick, very compact, and they should not be radiative, and so on. Keeping all these things in mind, tungsten and lead are the most suitable candidates. If you need to do really compact one, tungsten is the best choice. So in ALICE, there are two calorimeters. One is EMCAL, electromagnetic calorimeter. It is situated just after the top, and it is 4.5 meter away from the beam. Total coverage is for delta phi 107, and eta coverage is plus minus 0.7. Please keep in mind, unlike ITS, TPC, TRD top, it don't has full phi coverage. It has coverage, delta phi coverage only 107 degree. Please keep in mind. And it has 77 layers. Number of towers in layers is 12,288, there are modules and super modules. What is the main purpose of this electromagnetic calorimeter? To find electrons and photons, since they will be producing electromagnetic shower that I have shown just a minute back. And once you know these electrons and photons, you can have information about jet, which is the hard probe to understand the QGP formed in the collisions. And once you measure the jet, you know about the jet fragmentation functions. And if you know the jets, then you can have some information about photon jet measurements and also B jet measurements. And what is the technology that was used? As I have said, in calorimeters, one need to have an absorber and detector. As the absorber, here they used lead, and as detector, instead of silicon, they used scintillators. And these scintillators will produce light. So light need to be detected. Usual way of detection is photomultiplier tube, but photomultiplier tube cannot work in magnetic field. And this EMCAL is inside this cylindrical part, which is inside the magnet. So you cannot put photomultiplier tube. What is the way out? They have used APD, avalanche photodiode, semiconductor diode, to sense these lights. Okay, so this is what EMCAL do and how it look like. What about the other calorimeter? This is the photon spectrometer, and this is positioned exactly in opposite to the EMCAL. It is placed at 4.6 meter away from the beam, and it has limited azimuthal coverage, not like other central detectors, only 70 degree. And what is the eta coverage? Very less, plus minus 0.12. And there is a difference between FOSS and EMCAL technology wise. EMCAL has lead as absorber and scintillator as the detecting medium, but in case of FOSS, the same material is serving the purpose of absorber and also the detector, and it is the lead tungsten. So this is a composite material which is being used to serve both the purpose of absorber and the detector. And again, here this is a kind of scintillator, and it will produce light on incidence of a particle. So this light will be sensed by APD since it is inside this magnetic field. And again, there are about 12.5 K channels in these FOSS, and it can measure gamma and neutral mesons with PT in the range 0.1 to 100 GeV. So this is the two calorimeter that are that are there in the ALICE experiments. Now let us go over to the forward detectors. There are many detectors. Few were there. Now, they are not there, not working anymore, and few are still there and upgraded after this, LS2. One detector is PMD detector, which was an effort from India side, completely Indian detector. It was placed at 367 centimeter away from the interaction point in the forward direction. And what was its eta range? I have made some mistake. This eta range should be at 3.5 to 7. No, this eta range I have made a serious mistakes. This about 2.5 to say 4.5. Please, ignore this. 6.5 to 7.5 is a wrong one. And how it works? This PMD consists of 3 layers, and first layer is a detector layer, middle layer is a absorber, and third layer is a again detector layer. This first and the third layer, detector layers, they are consisted of many hexagonal cells filled with gas. So basically, this is a combination of gas detectors in proportional mode. And then, what is the methodology it will work? If a charge particle enters, it will give a signal and then passes through the absorber, do nothing, and again give a signal at the later layer. So one signal at the first layer and one signal at the last layer will tell you it's a charge particle. If it is a photon or electron, it will give, if it is the electron, it will charge particle, it will give one signal at the first layer, then passing through the absorber, it will produce a shower, just like calorimeter, and produce many particles. These many particles will produce many signals in the last layer. So one signal at the first layer and many signals in the last layer tells you it's the electron. And in case of photons, photons is not a charged particle. It will not going to give any signal at the first layer, but it will produce electromagnetic shower-like electron passing through the absorber. So many signal in the last layer. So no signal at the first layer, many signal at the last layer will tell you it's a photon. So this is the way of this photon multiplicity detector used to work. And there are a lot of data, and I guess many people are also analyzing this data these days. Okay. So we have stopped taking data during, I guess, 2018 or 19. So, and these detectors are back. If somebody is interested, he or she is always welcome to visit the ECC. Okay. After this PMD, there is a spectrometer called muon spectrometer. This is also a forward detector, and components are passive font absorber, just to absorb all hadrons and photons. And as the name suggests, it will only sense muons. So except for muons, anything will be garbage to it. That's why they put a very thick absorber which will absorb all other particles except muons. And then there is a tracking system which is made of 10 cathode pad or strip chambers arranged in 5 stations of 2 chambers each. All 5 stations has 2 chambers each. And special resolution is better than 100 millimeter. And also you need to have some trigger systems, and these trigger systems are made with these resistive plate chambers. Why resistive plate chambers? Because they are, time resolution is exceptionally good, of the order of say picoseconds, right? And also they use some dipole magnet, and they are positioned in the at 7 meter away from the interaction point. What is the main focus of this muon spectrometer? Main focus to measure the muons for PT greater than 4 GeV per C, and it can probe electron muon measurements as well with a reduced rapidity window, of course. And they study this J psi and psi prime, all these bottominium states like these particles. Okay, and what is the coverage? This coverage is like PMD 2.5 to 4, and not full 5 coverage, 171 degree to 178 degree, and the extent along the beam axis is minus 5030 to 900 millimeter. So there is, 2 more detectors which were earlier there, V0 and T0, but not now. The left one, the left hand side is for V0 detector. This detector was built with scintillator counters. There were 2 part V0A and V0C. They were positioned at 2 sides of the interaction points with the rapidity range as shown here, 2.8 to 5.1 and minus 3.7 to minus 1.7. And they segmented into 32 individual counters distributed in 4 rings, 8 sectors of 45 degree. And they usually used to be used to measure the centrality. So when you have events, what is the centrality of that event? How we used to measure? Just by, getting information from this V0 detector. And other detector is the T0 detector. As the name itself suggests, this consists of PMTs equipped with Cherenkov radiators, and it starts generation time for the top detector. So basically it gives it serves the purpose of a trigger detector. That that you should keep in mind. But both the detectors are not are not there anymore after this lockdown, this shutdown, long shutdown. Okay. What else? Then is the forward multiplicity detector. This is again, was there. It has some specific purposes. It used to provide the charge multiplicity, charge particle multiplicity in the forward rapidity domain, minus 3.4 to minus 1.7 and 1.7 to 5.0. And it has 3 major parts: FMD 1, 2, 3. Among these FMD 1, 2, 3, FMD 2 and 3, they were nearly at a same distance opposite to each other compared to this interaction point. and it has total 51200 channels. I mean, if somebody is looking at R1, run 1 and run 2 data, probably they will find this FMD data still there. But after this long shutdown, it is not there. Okay. Then comes HMPID. This is high momentum particle identification detector. Since this is a particle identification detector, usually, I mean, people used to use MWPC for that. You know that. And very high momentum. If it's a charge particle with very high momentum is always preferable to use a Cherenkov technique. That's why, I mean, this HMPID use this Cherenkov radiation and MWPC to detect, I mean, to identify some particles. So, you know, in case of Cherenkov radiation, how it look like. So when a particle in a medium moves with velocity faster than the velocity of light in that medium, then it will emit some radiation. This is called Cherenkov radiation. And this, due to this Cherenkov radiation loss, the energy loss per unit length can be expressed in terms of this. And I mean, you can convert it into signal once you let this Cherenkov radiation to enter your photo. I mean, this photo sensing instrument, and followed by MWPC. Actually, HMPID consists of three I mean, ring imaging Cherenkov counters of 1.4 meter by 1.3 meter each, and it extends the capability of Alice measurement for P by K and K by P on a track by track basis up to 3 GB and 5 GB for these two cases. Okay, so this is all about HMPID, and the next one is MFT. What is this? This is muon forward tracker. This is a new detector after this long shutdown. This is, I mean, this has been placed just before the muon trackers. And this is a very, I mean, this is a very new high resolution silicon tracking detector installed in front of muon spectrum. And it consists of two hubs cones containing 5 detection hub disks placed along the beam axis between 460 millimeter to 768 millimeter. And the technology they have used exactly the same technology that has been adopted by the present ITS. It means CMOS based MAPS technology, and the same readout methodology as well. Okay, and the pseudo-rapidity coverage it will have is minus 3.6 to minus 2.5. Then comes the FIT. As I have said, this V0 detector, T0 detector, FMD, they are there, and they used to serve the purpose of trigger detector. But after this long shutdown, there is no V0, T0 and all these things. But you need to have triggers. How can you do this? I mean, though we don't have V0, T0, all these detectors, but after this long shutdown, they have installed a new trigger systems. This is called fast integration trigger. And it has 3 parts. FTO, FVO, and FDD. What is the FTO? It has 2 parts. Based on these quartz Cherenkov radiators, time resolution is very good, 13 and these picoseconds, which is the necessary condition to be a trigger detector. And they have, I mean, it is at 3.3 meter away from the interaction point, and it has 24 modules. And if you look at the FT0C, it is positioned 84 centimeter away from the interaction point. What about FV0? This is a large segmented scintillator disk. See, Cherenkov radiator or scintillator or RPC, they are used to be used as a trigger detector. So here for FV0, this is a large segmented scintillator disk with mid-time resolution of about 200 picoseconds and very uniform response over the whole acceptance. And it has 4 centimeter thick plastic scintillators, and it is divided into 5 concentric rings of equal delta eta coverage. And FV0 deliver 48 independent readout channels. So it will definitely give very good, very good this trigger response. And the last one is FIT FDD. This has two nearly identical arrays, FDD A and C, surrounding the beam pipe on opposite sides of the interaction point. And each array has 8 rectangular scintillators. Again, this is of scintillators. And it contributes to the measurement of diffractive, either single or double cross sections, and studies of and help studying ultra-peripheral collisions. What is the use of these feeds? It will serve the purpose of interaction trigger, online serve the purpose of online luminometer, so it will measure the luminosity as well. Then initial indicator of the vertex position, and forward multiplicity counter. So, I mean, this is not the all that Alice detector has in the present setup. If I look at the list of the detectors and other subsystems in Alice, these are the list. So ITS, TPC, TRD, TOP, EMKL, FOS, HMPID, MFT, FEET, muon spectrometer, JDC, CTP, DCS, O2, and so on. And you can understand that we can reach up to half within this permitted time. I mean, we couldn't discuss about these upgrade projects or even these readout methodologies and how these data transfers are there, how these triggers are being processed. I mean, triggers are being flowed in during data taking and so on. Probably, if we get some time in future, we will discuss, or we get chance, we may have some more discussions in offline mode. Okay, but it will not be completed unless we say something about this ALICE-T. What is ALICE-T? This is the future of the ALICE experiment. At the present stage, ALICE detector has many detectors. They are using different kind of technologies, sometimes gas detectors, sometimes resistive plate chambers, Cherenkov radiators, or silicon detectors, or scintillator detectors, and so on. What is the projection like? This projection is, in future, ALICE will be using only silicon detectors. Starting from ITS, TPC will also be, made with these silicon detectors only, and then TRD or all the other detectors, NCAF, barrel, every detector will be made with silicon detectors. So probably it will be a good point to put more effort in getting experienced in this silicon technology and applying in our field, and that will be very much helpful in coming days.